everyone, and welcome to the Slightly Scientific podcast with me, Oliver.
Me, Stacy.
And me, Finley.
So today is really exciting because we are going to be interviewing Imogen McCurley, who has got a degree in biochemistry. So yeah, Stacy, do you want to ask the first question then?
So the first question is, what even is biochemistry?
So biochemistry is the area of science that explores the chemical processes within and related to living organisms. So biochemistry focuses on the processes happening at a molecular level. So that means it focuses on what's happening inside our cells, studying components like proteins, lipids, and organelles. It also looks at how cells communicate with each other, for example, in growth or when you're fighting illnesses. Biochemists need to understand how the structure of a molecule relates to its function, which allows them to predict how molecules will interact, basically.
It's kind of like the chemical reactions inside the cells.
Yeah, exactly, because a lot of biology, I guess, focuses on like the bigger things. So yeah, processes that are a bit more obvious, but this is really zooming down at the chemistry inside cells, because at the end of the day, everything that drives inside your cells is just chemistry and is reaction. So it's more like biochemistry is very broad, so you can study the immune system, or you can study energetics, or you can zoom in as kind of as far as you want to, even to like single reactions, but it's pretty cool.
So biochemistry, there's something for everyone because it's so, wide.
Yeah, exactly. You can, for example, at university, so I went to Exeter, but in first year they kind of give you broad modules, so some chemistry ones, we did like biophysics and stuff, but in your second and third year you can like kind of go down whichever avenue you want, and there's loads of them. So it's a very broad topic, but it basically is the science that is going on at a molecular level, really zooming in to your cells and everything like that.
That's really cool. Yeah.
So how does it affect us? Like, if it does, how does it affect just a normal human being and how they live their life?
So I'd say that biochemistry occurs in every aspect of your life, whether it be processes in your body or in the world around you. So these processes occur in every living thing, but also I'd say in our interactions between living and non-living things. So biochemistry can also be found in synthetic processes, for example, like drug design. So drug design is obviously like a non-living process, but because drugs need to be designed to interact with living cells, you can study it from a biochemical perspective. So therefore you can use things like enzymes, which you take from living organisms, to manipulate and change chemical structures of drugs at like a tiny level, really precisely, so that they interact with our bodies in a certain way. Even me speaking right now could be analysed in a biochemical way, sort of like your nerve impulses making you talk. You can analyze the different chemicals that are used at your nerve endings, so they're called neurotransmitters. So it can also be used to tackle things like climate change, to make industrial processes more efficient, and it can be also used to explore, like, for example, ways to like take carbon out of the atmosphere. I'd say it can be found in every single aspect ever. It just depends on where you look, kind of thing.
Yeah, that's really interesting. Yeah. So
amazing.
Has that also got to do with something? So I've heard that scientists, they're using an enzyme called like PETase to like break down PET. Is that also something like that you can like study in biochemistry?
Yeah, so like for that specific example, I have heard of it. I don't know a lot about it, but there's for example, if you, like, insulin, that's a molecule that's used in our bodies in many important ways. So for a long time they couldn't figure out how to, for example, synthesize insulin easily, and they found out the best way, and this is used in a lot of ways in science. So you get a big vat of bacteria basically, and bacteria are very good at taking molecules in their environment, taking them in and making them into something else. But obviously bacteria are very limited in what they can make because they're bacteria. But what you can do is you can genetically engineer bacteria so that they start producing enzymes like human enzymes or horse enzymes, so that if you put the right ingredients in their surroundings, they'll literally take it in and make the thing that you want. So I guess using enzymes, which is like biology's tool, is a way that you can make literally anything. So that is an example of biochemistry, and you could study that at university. You could do your dissertation on that, I don't know, but it's very, once you start opening up doors on what you can do with biochemistry and molecules, I think it's big. It opens lots of doors. So that's the way that insulin can be made now, is with bacteria, which is quite good, cheap, and you just put it in and it's made.
How did they make it
Before?
How did they make it before?
I don't actually know, but I think it was very difficult. So obviously insulin can be used to treat diabetes, and that's one of the reasons why diabetes killed and wasn't really a disease that people could, survive beforehand. They had no way of making insulin. I think they took it directly out of dogs or something really weird, or like horses. But if you're going to put dog or horse insulin into a person, that's not going to go down well. I don't know, it could be something to look into, but it's an area that's really cool.
Yeah, and your dissertation was on fungal vaccines.
Yes.
Right.
So fungal diseases don't really affect many people that badly. So you might have heard of like athlete's foot, stuff like that.
Yeah.
Oh yeah.
So like little, like you can get fungal like skin infections. They're called like superficial infections. They're the most common type of fungal infections, and they don't really affect people very badly. But what you can get in people with like HIV or immune suppressed diseases is you can get really bad like invasive fungal infections. So
really?
So people with HIV often suffer from a type of lung infection called aspergillus, and you'll literally get these threads of fungus. It's pretty gross, sorry, but sort of threading through your lungs. So like a fungus can basically go in deep into your body and sort of colonize your tissues because people with HIV or cancer, your immune system is really weak. And so something that would never affect people like us would now have the power to kind of overtake your body. So I was kind of the treatment for fungi is not very good. It's very expensive. It's very toxic because, and you guys probably don't know this, but like fungi are also eukaryotic organisms. So, you have us, which is eukaryotes, like us plants eukaryotes, yes,
yeah.
and animals, and then you have bacteria. So fungi are eukaryotes, which means that drugs that are designed to kill fungi may also have like bad implications on our cells. So they're not very good. So I was trying to look into potentially creating vaccines for fungi, but I had quite a lot of issues. So for example, there's fungi all over in our environment. So you don't want to start overstimulating your immune response to things that you're going to come into contact with all the time. And also people who have immune problems like HIV and stuff anyway, they're going to be harder to vaccinate because you need kind of a good, robust immune system in order to vaccinate people anyway. So that's kind of what my dissertation was on. But it was very cool. But I think the thing I found was that there are a lot of like leads, but a lot more research needs to be put into that area for they to become possible.
So I've never actually heard of like fungal vaccines. I mean, there were like, of course, viral vaccines. Is the process is the process of fungal vaccines kind of the same to make with viral? Or are they like completely different?
Well, there's lots of different ways. So with vaccines, you've got lots of different types. So you can take the pathogen directly and edit it a bit to make it non-pathogenic. They're called attenuated, which means that you make the pathogen very not as harmful, but it's still the key components of it are still there enough to evoke an immune response. You've got peptide vaccines, so you take bits of protein from the virus or the fungus and that's what you put in, or you have live vaccines where you take literally the living thing but you might take a single component of it. So I studied 3 main diseases, which is candidiasis, cryptococcosis and aspergillosis, and they're kind of 3 big genre of fungi, but between each one there's loads of different ways you can make vaccines. But there is overlap between viral vaccines, but I almost would say viral vaccines are more simple to make because more people are affected by viruses. So your main focus is on the normal population rather than these people with cancer or HIV who are very hard to vaccinate, obviously, because their immune system. Also, you don't want to give someone a vaccine which you think, oh, it's fine, it's not going to harm you, and their immune system's rubbish. So actually it does. So a vaccine that would never harm any of us, but would harm them. So it was a really interesting topic, but a lot of loops to get through because it wasn't that simple. Do you know what I mean? They haven't got a clear-cut answer yet.
Yeah, and it's still in research today as well.
Yeah.
That's why I chose it. I kind of wanted to do something new. So I basically looked at every single fungal vaccine that had ever been made since like the 1930s and made like a big table of them. So it was just something quite new, which I found quite exciting. But that's the nice thing about university. I feel like there is opportunity to explore stuff that isn't very well known about or researched about. It's quite cool because it's hard because you got to look deep into the web for all these articles, but there's opportunity to really feel like you're like discovering something.
Yeah. Where do you think this is going to go in the future? Like, what do you hope and think is going to be done next with?
Yeah.
I don't know. It definitely needs some more funding, because unfortunately sometimes with science, like nothing's going to happen unless you chuck a load of money at it. Like it is expensive to do research, and so you almost need a big enough demand for the vaccine. So it depends. It depends whether fungal treatments get better. If fungal treatments get better, maybe there won't be as much demand. And if some of these diseases can start increasing in severity, because you get a bit like you get antibiotic resistance, there's also emergence of antifungal resistance. So like the pills that you can take for like candidiasis, like athlete's foot, or the creams like funguses, because they're being used so much, are getting resistant. So it all kind of depends. I think if medicine for fungi improves, then I don't know how far it will go. If it doesn't, then there'll be more of an emphasis, and then people might look into this a bit more. I don't know, maybe there'll be a big discovery, because it will definitely improve the lives of AIDS patients and people with cancer.
Yeah, that's really good.
Yeah.
I don't know how to react to that, because like obviously we are not affected by it. We don't have HIV or cancer, so we don't have a weakened immune system. But for the people that do, it must be like, because there's no actual treatment out yet. There's like, if they get one of these a fungal infection, there's nothing that can then treat them.
Yeah. There's some stuff out there, but it makes them quite sick. So it's weird, because it's something probably people don't really ever think about. But these invasive infections can be pretty horrible. And like you can get them in your blood as well. It's not very nice, but and they're quite common, found in like hospital settings. But yeah, it's interesting to think it's something that people probably don't ever think about. But yeah, so that's why I wanted to look into it.
But I do think it's nice that there is like hope for people with HIV, that one day there may be a cure to all of this.
Yeah, exactly. Because I think with HIV, the HIV targets your immune system. So it infects and kills a type of immune cell. So usually people with HIV, they don't die of the HIV itself. They die of, they're called secondary infections. So that can be bacterial infections or fungal infections. But yeah, it's so now obviously there is treatment that suppresses the HIV, allows people to live with HIV, like antiretrovirals. It stops the HIV from replicating, but it's also nice to focus on treatment for the secondary infections that are also harming people.
So how do these fungal vaccines like actually work? So on like the molecular level, how would they stop the fungus from spreading around the body?
So there's lots of ways. So treatment, usually antifungal treatment sort of it can do lots of things. So it can stop cell replication, it can punch holes through the cell wall, cell membranes, and cause like cell leakage. So that's how the treatment works, but obviously you don't want that to happen to our cells, so that's where. But the fungal vaccines, it's all about training your immune system to kill the fungi before it harms you. So for example, like let's take a peptide vaccine. So that's taking a protein that you'd usually find in a fungus and putting it into you as in a vaccine form. So your immune cells will see this as sort of like a foreign invader, and they will bind to this protein, see it foreign, and then create an immune response against it, but also create what's called immune memory. So it means that if you were ever to interact, like come into contact with the thing in real life, you've already got these immune cells, like these memory cells that can like are ready to fight. If you kind of see it like a little army, it's introducing the protein to your body, thinking foreign invader, creating this little army against it, so that when you come into contact with it, you're almost ready and you can kill it straight away before it makes you sick. Obviously this is a bit hard if you are suffering from a disease where your immune system is weak. There are other things around this. You can like amplify your immune signals. So your immune system sort of communicates as a big network. So you can use molecules as almost like signals to get it fired up. So there are things that can help enhance your immune system, but what you want to be careful of is not triggering this army into everything you're coming into contact with in the environment. So that's where you can see where it's going. It's kind of like a loophole, which is why you almost need like a scientific breakthrough to kind of overcome. But there are little ways that could be looked into. So it's just like helping your immune system, or like maybe using those signals to amp it up more before you get sick with the fungus in the first place. If not, there are those treatments I talked about, but yeah, they're not amazing. They're not that great.
Are there antibodies for fungus?
Yes.
Oh, I thought it was just for viruses. And
No. So a specific type of immune cell, it's called a B cell, is responsible for producing antibodies, and antibodies have loads of different purposes. So obviously they're a protein, they're a Y-shaped protein. So if let's say I've had this vaccine, I've got some immune memory. So what happens is the protein that we were talking about comes in, the B cells bind to it, kind of take note of it, and then they will produce these antibodies, which are a perfect fit for this protein. So when the real fungus comes in, your B memory cells are sort of fired up, produce this antibody rapidly. So you're not producing these antibodies all the time. A few of them may float around, but it's when you come into contact with the real thing, they're sort of fired up. And then these Y-shaped proteins, the antibodies, can bind to the fungus. And what it does, so antibodies, you can get into viruses, bacteria, everything. So they've got like different properties. So like they can bind to bacteria and sort of all stick together and make this sort of mesh. So effectively, you're just clumping all of the fungal proteins, cells, bacterial cells, whatever the antibodies for, you can clump them together, which makes it much harder for them to float around your body, causing damage. They act like a signal, so they can take white blood cells over to them. They're called phagocytes, so that you can like gobble it up. So there's loads of different ways. On viruses, they bind to it, they do the same thing, or they can mark fungal cells for like cell death. So they're amazing protein, considering that this is another thing I find cool about biochemistry. That's a single protein and it can do so much, and it can also be used in signaling. So basically it's an immune protein which has so many powers, but it can be used to trap the pathogen, bring your immune system towards it. So you can get antibodies to fungi as well, and that can be a way that, again, that your immune system is sort of ramped up and ready for this for the pathogen to come, kind of thing.
There's such thing as plasma therapy for COVID-19. Is that Are you able to use plasma therapy for fungal for fungal infections as well?
Yeah, so I kind of for COVID-19, it's basically taking a component of your blood, but you can kind of use that broad avenue, and it's called passive vaccination. So maybe you vaccinate, you prime a healthy person's immune system, so you get it all ready. And technically you probably could transplant some of that immune system from the healthy person into a person that's sick with HIV or cancer. So that is an avenue. That's sort of like one of the solutions that I found in the end. Like maybe if you can't vaccinate these people who are ill with HIV or cancer, maybe you could vaccinate a healthy person and see if you could move some of that across. But usually taking blood plasma is a bit easier, but maybe taking other components of the immune system is a bit more invasive procedures. So it's definitely something to look into, but obviously taking blood out of people and vaccinating them and all this stuff is quite difficult. It's expensive, basically, but that's definitely an option that you could look at.
Oh.
What's the most challenging or like difficult part of making these vaccines, and in fungal just what you're doing in general?
It's probably, so the research, obviously, to start off with, is challenging just because you're presented with a blank piece of paper and you think, where the hell do I look? Which part of the fungus are you going to focus on in the vaccine? And also you're going to look as well at in these vulnerable patients, so patients with HIV or cancer or things like that, you have to be very careful that you're not vaccinating them with something that, as I said, you might think is fine and actually could make you ill, because you haven't attenuated it enough, which means you haven't removed that pathogenicity enough. So there's a challenge of, it's called vaccine reversion, and there have been cases of it in history, not in fungal vaccines, but in vaccines in general, where I can't remember, maybe it was plague or something like that, I can't actually remember, but they gave people the vaccine thinking it's fine, and it was like a less pathogenic version, and then it reversed, it mutated back to the pathogenic form. So that is something you really want to avoid. So that could be quite a challenging part. And I guess also like just being able to evoke that strong immune response from these people that are suffering from HIV or cancer, it's hard, and you don't want to have to keep vaccinating people once a month, and you want to have a strong vaccine that works but doesn't make people ill, so not too strong, and also a vaccine that there's a lot of, it's like a fine balance, I'd say, and so good enough to work, not good enough, not too strong to like evoke allergic reactions and stuff like that. So it is difficult, and just making it stay, really.
What do you think will happen if someone was given like a faulty vaccine of something that can spread really easily, and then it mutates into something even worse?
Unfortunately, there's not a lot you can do where it's happened in history, and it is very rare. Like, I'm massively pro-vaccines. Like, I don't want anyone to think I'm being anti-vaccine. Vaccines are amazing and great, and they are I think one of the best scientific discoveries ever. But in the past, when it has happened, it's very, very rare. All you can do is quickly get the treatment out. Like with most diseases, vaccine is preventing and treatment is curing. So a massive apology first, and then quickly going out and treating these illnesses before they get too bad. But it is rare, but if it happens, this is why though things go through so many years of trials. I know with the COVID vaccines a bit different, but they have put in probably like 10 times the amount of hours and people. So, and they've tested it on 45,000 people. So I'm not too worried about that. But most vaccines go through a few years of trials, and and they test it on everyone. So first they'll test it on the normal population, and they'll test it on people prone to the disease and like work their way down. And they have to make sure it's good with everyone. But yeah, if that ever were to happen, just got to get treatment out quickly. But it's very rare because they are so careful with these trials. And that's why so much research goes in. Like if you were to release a fungal vaccine, chances are it's probably gone through 20 years of research before it ever comes out, because they do need to be so safe.
Right. How expensive is it if they came up with a fungal vaccine that like is really good, how expensive would it be to mass produce it?
Oh God, well, the research itself is really expensive. I don't know, to be honest, but what usually happens is people come out with an idea and they patent it. So it means that they like copyright it, and then it usually gets bought up by one of the big pharmaceutical companies. So unfortunately, science is really expensive, but that's why you get what's called grants from the government or from scientific organizations or charitable organizations, which allows people to do the work. So getting to the idea itself is already really expensive, and then once you have that idea, let's say someone found one, it then would be up to the pharmaceutical company to buy that idea and start producing it, and then they'll have to sell it for a profit, because at the end of the day the pharmaceutical companies are a business. But that's why healthcare is so expensive, I think. And then after a few years, things always get cheaper because you get better at making it, but the process becomes more efficient. And so like things are always really expensive when they come out, and that can be anything from like cancer treatments to anything. Then after a few years, they start to die down, especially as the patent starts to run out as well. But yeah, I'm not sure, but expensive basically.
Cool.
Mm-hmm.
I think Stacey, do you want to ask your second question then?
Well, you have talked about this a bit, but how could biochemistry be useful in like improving the world in other ways?
So I think it's like general, because like we kind of talked about the vaccine.
I think in so many ways. I think biochemistry is one of the most important fields of research and discovery right now, because it can be used to improve well, I think, in any ways. For example, take right now, the people making the COVID vaccine, that's biochemistry, and that would be something that saves everything, our social lives, our economy, our mental health. So that's one way, and just in healthcare in general. But I think biochemistry could also be used in like things like the environment, as I mentioned. Like for example, farming is one of the biggest industries which produces greenhouse gases, and basically nitrous oxide is a gas that is 300 times more like damaging than carbon dioxide, and is also damaging to the ozone layer. And what happens is when you put fertilizer on the soil, there are certain bacteria within the soil that will take that nitrous oxide and take nitrogen and convert it to nitrous oxide. So basically what you can do is find chemistry ways or like biochemical ways within the bacteria to prevent them from producing this nitrous oxide. So that's some things. And you can also use it they're trying to discover it to make like new fuels, like split water to use hydrogen as a fuel instead. So I think just every way possible that you could think of, I think biochemistry could be used. Just science in general, to be honest, is like just genetically editing things and just changing things could like have so many avenues. Like it's like a deep hole to go into. But yeah, and even in things like people's health, like exercise and diet, you could even analyze that at the biochemical level to produce like improve people's well-being and stuff like that. So I think just every way, and that's, if you went on to study something like this, you can go down all those different pathways. But I know, at least from my university year, the research people are doing and like people that have gone on to do masters and PhDs, the things that they're discovering is absolutely amazing, and technically all of them can be used to be counted as improving the world around us. So sorry, that was quite a vague answer, but I think that's like in so many ways.
I never knew biochemistry could be involved in so much of our world.
And use so much to help so many people.
No, it's cool. I think it's not very, people don't really know what the word biochemistry means. Like even when I was looking into this degree, I was like, what does it mean? But it literally just means studying the chemistry of like everything, and like the biological reactions, but that can just be used in any way. Like I did modules in my third year on like drug design, which was really cool, or like environment stuff. So it's very broad. It just basically means that you're zooming in on the science, but it can be used to study literally anything.
That's so cool. Yeah. Finny, do you want to ask your question then?
Well, would you recommend people studying this? What would you recommend that people go out to university, study biochemistry for?
Yeah, absolutely. Like definitely. I think it's a very broad degree. Something like natural sciences is a bit more broad. So that means you can study maths and the 3 sciences. But biochemistry, I really like because it's broad, but it's still quite specific. So I absolutely would recommend studying it because I think there's just like a niche for everyone. You need to have a bit of like a passion for chemistry and biology. There's no point studying it if you're like, I hate science, like don't do that. But if you do like science, definitely, like you can study anything from ecology to immunology to like physical and medicinal chemistry. Like I did modules on like bee behavior, but I also did modules on the immune system and drug design, and then I did modules on like energy and kinetics. And I think the beauty of it is you can just choose anything you want to learn about, especially as like at a big university like Exeter. They have so many modules that you can pick from. The only bad thing I say about it was that there wasn't a lot of maths when I was there, but I know they're changing this now. Like Exeter is changing it so that there's more maths in the course, because even if you're a biologist, maths is really important. Yeah, there's literally options to study anything you want. And yeah, it's just that broadness, but that specificity as well. So yeah, I definitely recommend studying it. And it also sets you up with loads of skills, to be honest. Like my job that I'm going into for next year, so I'm on a gap year right now, but is actually finance. So even though the university will encourage you to do that, go down that research route because it is really interesting, like it's just a degree that sets you up with loads of different skills. So it develops your writing skills, your analytical skills, your presenting and communication skills. So it's very attractive to employers. You can literally go into anything you want. And I'm thinking, so I'm going into working for a big finance company, but I think maybe after this I might go back to biology or biotech or biochemistry and do sort of finance or investment for science is kind of what I want to do. I just want to get trained up at a finance company first. So like there's so many different options. So I think it's a very well-rounded degree.
So that's really cool. When did you decide to take biochemistry, and also what A levels did you do?
Okay, so I did maths, further maths, biology and chemistry. So I originally was actually going to do a maths degree, and then I wanted it to I just wanted to do something a little bit more interesting, to be honest. I'm not saying that maths isn't interesting, but I just wanted something with a bit more like substance. But I don't know, I kind of, with my A levels I was thinking maths or natural sciences or biochemistry, and in the end I don't really know, I just really liked how broad it was and how I looked at the different universities, different courses, and I was like, I really like the modules that Exeter gave. So yeah, I kind of fell into it. I think in a lot of things in life, sometimes you just fall into it. I loved science and maths. That was definitely my kind of subjects. And I thought, what can I do these A levels? And I kind of fell into it, but I'm definitely very glad I did. But when I was that young, I was like, I do not know what I want to do. So I'm not going to lie to you. Part of me just fell into that. But no, it was very great. I feel like it's really hard when you're young though to know what degree to do. You're not told a huge amount about it at school. You're just kind of told like these are the core subjects you do. So it is really difficult, and I definitely found it difficult. But yeah, I guess it's just like researching, reading all the degree programs and seeing that there's actually so much out there that you can do, and it's not just like core sciences, bang, bang, bang. But yeah.
Did you so because we're coming up to our GCSEs now, did you take triple sciences, like all 3 for GCSEs? Or did you just?
No, yeah, I did.
Yeah.
I don't know. I didn't very like English very much at school, but I did like languages like French and Spanish. Like to be honest, when I was doing my GCSEs, I knew that I was good at maths and science, but I wasn't really like set yet. But I always found it very interesting. Physics I found a little bit less interesting. I'm not going to lie to you, but I think that's just because I found it more like abstract. But I have done a few physics modules at university now, and I'm like, I probably should have like thrown myself into that a bit more. But yeah, no, I did triple science. But I was still not, I didn't know I was going to be like a scientist yet at that age. So there's still hope, guys. So, maybe, I don't know.
Yeah. This is kind of backtracking, but say some patient came to you with some really bad fungal infection. What would be your first steps to counter this, to help them?
It kind of depends what type of person they were. So like people like you and me can still get quite bad fungal infections. And by the time you have the infection, it's a bit late to vaccinate, and also there aren't any vaccines out at the minute. So I guess it would just kind of be like starting on that treatment. And they're called azoles, the type of treatment that people go to straight away. Like most one for like the type of fungal infections people like you and me be getting, we'd be taking fluconazole. So I do a course of antifungals like that. But in people with really, really bad infections that maybe might be antifungal resistant, you kind of have to go in with 3 different types of antifungals. So you've got the azoles, and there's 2 more types, and one of them is quite harmful. But I guess it depends on the severity of infection. You'd always try with that first route first on the fluconazole, and then you'd look at other treatments. But people like you and me, we'd be fine. It'd be the people with immunocompromised, you call them, with a lower immune system, that'd be a bit more worried about. But there is treatment out there, it's just not great. So you just kind of have to kind of bombard people with it, but it can be a bit toxic sometimes. But like in this country, not many people die from fungal infections, like maybe a few, but it's actually more of an issue in countries which don't really have that treatment readily available. In countries where HIV is quite high, so like in the continent of Africa, I know that it's a bit of an issue, which is sad. But so I guess it's just getting that treatment sorted as quickly as you can.
What kind of jobs can you get using it?
From biochemistry?
Yeah.
Yeah, so literally anything, as I kind of said, like anything you want. So people go on to do, if you want to do research properly, you probably need to go get a master's or a PhD, probably master's minimum. So a lot of, like, for example, people in my cohort, a lot of people are going on to do masters, and in these masters you kind of specify even more. So it wouldn't just be a biochemistry masters anymore, it would be a masters in something where you're working with a certain professor on some research. So like marine biology masters, or like immunology masters, neuroscience masters, do you know what I mean? So you specify again, so people do stuff like that. But I know people that go in to do even like law conversions, they go into like medicinal law, or people like me who go into finance, people that go into banking, people that go into the military, people who go on to do literally anything. Because for example, like we're just taught a lot, so there is still a lot of writing in biochemistry. Like that was the bit I found the hardest, I think. Like I didn't do any written A levels, but I did do EPQ, which you do in sixth form, which is like an essay type of thing. But there's a lot of writing, there's a lot of analysing data, there's a lot of stats. You've got to present, like I had to present to a whole lecture theatre of people about 5 times, because you're like, right, we're doing this project as this is part of your module, and you develop those talking skills. So as I said, like it kind of just sets you up to do anything. And because it's quite a hard degree, like it is hard, it's really interesting, but it's challenging. Because it's a hard degree, people like it's well respected, because it shows that like if you've done well at it as well, shows that you've sat there and you've really like thrown yourself into something. So literally anything you want. If you want to go into science, it's a great degree. If you want to go into like financy stuff, it's great. And you can always go on and retrain, a bit like the law thing I talked about. Like if it's giving you that kind of sciencey background that you like, but you want to do something different, then great. Like what I realized from studying at uni is that you can always go on and study again, and you can go on and study more, something different or something more in depth. So literally anything.
So I am not a massive fan of English and creative writing and comprehension. So how much writing do you have to do? Is this like in all degrees, or in most degrees anyway, do you have to do like a whole writing section?
Yeah, to be honest, with any dissertation, so that's my dissertation was about 12,000 words. So that's a lot of writing. But what you'll come to realize is scientific writing is very different from creative writing. So like it's very factual. It's less of that flouncy language, and it's a style that you develop. So especially from like reading scientific articles, if you think about it, all the articles that are written or any of the journals and magazines, like someone's got to write them. Usually if you submitted a scientific paper, like if you did your own research, it then goes on to review, and someone who's actually good at writing would then go and have a little edit. But so you don't have to be amazing. But they have whole journals, which is the thing that you publish a scientific article in, have this whole team of people that help you with the writing stuff, so don't worry. But no, there's a bit, and you've got to write essays, but it's not English essays. Like if an English person read my essay, they'd probably be like, what language are you speaking? They one, probably wouldn't understand a word of it, and 2, they'd be like, this is rubbish. But so don't worry, it's a different kind of writing, and it's a writing that they teach you to do and that you pick up from reading science, but it's not like flouncy writing. It's just very to the point, so it's fine. You don't have to be some Shakespeare. And they do help you. Do you know what I mean? They teach you with everything that you learn at uni. People come from all over the countries, from all different types of schools. So in your first year, they try and get everyone up to the same level, and they help you. So like I hadn't written in years, and I was like, but it was fine in the end. I still got like a first on my dissertation, even though I cannot write. So don't let it put you off. And like, yeah, in most degrees there is writing. Maybe maths there's be less, but I know all like natural sciences degrees and stuff, there's gonna be writing in everything, because when you discover something, you've got to be able to write it down, I guess.
Yeah, of course.
Mm-hmm.
Thank you so much. That's all our questions. We got through it all. That's so good. Thank you so much, Imogen, for agreeing for this interview and answering our questions.
My pleasure. Thank you for talking to me.
Thank you so much for listening. Make sure to follow us on our Twitter and Instagram at The Slightly Sci and The Slightly Scientific Podcast. And be sure to have a slightly scientific day.